Hey everyone, today we'll get an understanding of continuity using calculus. Let's get right into this. So from before calculus, our understanding of continuity is basically being able to draw a graph without picking up your pencil. But really, what does it mean to not pick up your pencil? Well, it means that as you get closer and closer to a certain point, and as you just move along the graph, the function approaches what it actually is. So if we move along here, it approaches what it actually is. If we move along here, it approaches what it actually is. So with calculus, we can kind of describe this approaching a value as just a limit. So that means to be continuous, your limit has to be equal to your function value. That's how we don't pick up our pencil, and in other words, that's how we are continuous. Therefore, a function is continuous at some x value at x equals a whenever the limit as x approaches a of f of x is equal to the function value at x is equal to a. And this actually makes for a really good pickup line for you nerdy peeps that goes like this. Hey, does your limit equal your function value? Because I see us being continuous. Use that at your own discretion. So now let's review the discontinuities that we've seen before and prove more precisely that they are discontinuities. So for removable discontinuities, we see that the limit as x approaches a of f of x is not equal to the function value at x is equal to a. So since these aren't equal, our rule for continuity doesn't hold. It could also be the case that f of a isn't even defined in the first place. So f of a is undefined. And the reason why that's an issue is because if the function value is undefined, it can't even be equal to a limit value in the first place. So continuity cannot hold. For jump discontinuities, we see that the limit as x approaches a from the left side is not equal to the limit from the right side. So if the limit itself as x approaches a of f of x does not exist, well then it doesn't have a value to be equal to f of a in the first place, so continuity does not hold for jump discontinuities. For asymptotic discontinuities, well f of a isn't even defined in the first place because of that vertical asymptote. And if f of a doesn't have a value associated with it, well then f of a can't be equal to the limits because there is no value, so continuity does not hold. It could also be the case that one of the one-sided limits goes to positive infinity and the other goes to negative infinity, like we see over here. So if the two one-sided limits aren't equal to each other, the limit itself doesn't exist. So the limit as x approaches a of f of x does not exist. So in either one of these situations, there is no value to be had, so equality cannot hold, and neither can continuity. There are certain classes of functions that are continuous for every x value in their domain. Polynomials are an example, where we have functions like f of x is equal to 2x squared plus 1, or something like the green graph you see. They're actually continuous for all x values. Root functions are also an example, like f of x is equal to the square root of x. For all x values in their domain, they're continuous. The same applies for rational functions like f of x is equal to x minus 3 over x minus 5. They're continuous for all x values where you don't divide by 0. Trigonometric functions like f of x is equal to tangent of x are continuous for all x values in their domain also. Exponential functions like f of x is equal to e to the x are continuous for all x values in their domain, which happens to be all x values. Logarithms like f of x is equal to the natural log of x are continuous for all positive inputs, which is their domain. If we have two functions f of x and g of x that are continuous at x is equal to a, then that means their sum, their difference, and their product, along with the scaled version of one of the functions, will also be continuous at x is equal to a. When we divide by the two functions, well, we have to be sure that g of a is not equal to 0. Otherwise, we divide by 0 and lose continuity. And for composite functions, we need to make sure that whatever value of g of x we plug into f of x, in this case g of a, since we're checking for continuity at x is equal to a, makes f of x be continuous. So I want to talk about a special property of continuity. So first, let's remember that if the limit as x approaches a of f of x is equal to f of a, then that directly implies continuity. So that also necessarily means that if a function is continuous, then its limit as x approaches a is defined, and its function value is defined. So here's a special little diagram for us to think about that. So here at the top of this pyramid, we have the fact that f of x is continuous. And notice how having this pyramid have this top here actually depends on the fact that we have this foundation. And the foundation is that the limit as x approaches a of f of x exists and the function value is defined. So that means that if the problem tells you that f of x is continuous, then you can automatically infer that the limit as x approaches a of f of x exists and that f of a is defined. But if a problem tells you that the limit exists or that the function value is defined and they don't give you any relationship between the two of them, then there is nothing that you can think about in terms of continuity. That just about wraps everything up. Thank you for watching and have yourself a great day.